A very good morning to all of you. Today we are going to discuss on game search. This is week 4 part 5. So we will discuss heuristics in games, min-max search procedure and alpha beta pruning. So first we will see what is adversarial search. So we till now we have seen informed search and uninformed search techniques. So here when you are playing chess or ludo, so you are playing alone? No, right? There is an opponent. So in these problems, the success of one player means loss of the other. So this is called a adversarial environment. So adversarial search means decision making in presence of opponents. So mainly, the adversarial search means there is more than one agent. So each agent has different goals. So each agent's actions affects others' outcomes. For example, we know that chess there is a white and black will be there. For tic-tac-toe, we have X and O is there. So in multi-agent competitive environment, agents have conflicting goals. So that giving rise to a adversarial search problems commonly modeled as games. In AI, we mostly study two-player games. Two players means max and min. So max moves first, then min. So the players move alternatively. So one player gains means other player lost his game. So here, is it possible to represent a game like a search tree? Yes, that is possible. So each move leads to a new state. Here, the goal is not just a solution, but the best solution against an opponent will be the goal. So, game is a special type of search problem where the environment is adversarial. So here a game can be formally defined as a kind of search problem with the following elements. We will see the elements. First one is S0, that is the initial state that describes how the game starts. For example, tic-tac-toe, empty 3 into 3 board, chess standard piece arrangements we can consider as the initial state. And so S0 is the initial state that specifies the starting configuration of the game. And next is players. That tells who turn it is in next state S. So that can be either max or min. So if X started the play, then the next player will be O. So decision making depends on who controls the move. And next is action. So all valid actions possible from state S is the legal moves or actions. So illegal moves are not allowed. For example, tic-tac-toe, empty squares, legal piece moves only. So then action returns a set of all legal moves available in state S. Then next is result. It defines what happened when an action is taken. So it produces the next state. So place X on top left. That means in the case of a TikTok problem, it places X on the top left. So that is a new board position. So here the result defines the state resulting from taking an action A in state S. Then next is terminal. So checks whether the game has ended. So here the terminal states include win, lose or draw. So 3x in a row in the case of a tic-tac-toe problem, that is a terminal state because that corresponding player wins. So the terminal state that returns true if the game is over and false otherwise. Then next element is utility. Utility S comma P. That is the payoff function that assigns a numeric value to the outcome and defines only for the terminal stage. So if we can say that win is +1 and loss is -1 and draw is 0. So if the max wins, then the utility S comma max will be equal to +1. And for the min wins, then the utility will be that will be -1. So the max tries to maximize the utility and min tries to minimize the utility. So that means the utility S comma P is the numerical payoff of terminal state S for the player P. What is a game tree? So a game tree is a tree representation of a game where nodes are game states and edges are possible modes. So here we can see the initial state, actions, and result functions together generate the entire game tree. So in this figure, we can see that here each node represents each stage. And so here the each node represents a board configuration. That means each state. This is a tic-tac-toe board. And every box here we can see is one possible state of the game. And the edge that actually corresponding to each move. So each branch corresponding to a legal action. So moving from one board to another by applying some action. So we can represent it as a result of S comma A. S is the state and A is the action. So an edge shows what happened when a player makes a move. So we can see we can have a root node at the top. You can see this is the root node. So this is the initial state. And in the case of tic-tac-toe, initially the initial state means empty board. And then the player we can represent it as max of x. That means max will mark x on the board and the opponent is min. And min will actually put a O on the board. So here the game starts here. That means at the root node and max plays the first and uses the symbol x. And then the first level, you can see that this is min's turn. So after max places x in one position, you can see these are the possible, this level shows the possible location of x on the board. And then after max places x in one position, each child node, here you can see each child node shows a different possible x move. And the next player is min. You can see after max, the next player is min. So after max moves, it becomes min's turn and min will respond optimally. So here you can see that max and min they play alternatively. So the tree alternates between max and min levels because the players take turns. So here finally we have a terminal nodes. That means terminal level there are terminal nodes. Here the game ends here and here we will have the decision win, loss or draw and no further moves are possible. Here you can see the utility values -1 0 +1 etc. So utility means +1 means max wins, -1 means min wins, 0 means there is a draw. So these values comes from the utility function. So min-max works by propagating utility values from the terminal nodes and then start upwards. So that we will discuss in detail in the case of min-max algorithm. So min node chooses minimum value and max node chooses maximum value. And the root decision gives the best move for the max. So max assumes min will always try to hurt max score. So that's why min actually chooses maximum value and the max actually chooses the maximum value and min chooses minimum value. In adversarial games, the goal is not just to make one good move, but to have a strategy of every possible opponent response. So a contingent strategy is a complete plan that specifies what Max will do in every possible situation. So here, if Min does this, then Max does that. And if Min does something else, then Max responds differently because they are opponents. So Max choose a move in the initial state. So commonly you can see that Max chooses a move at the first stage or initial stage. Then min responds optimally. Then max again choose the best move. This continues until the game ends. So max plans assuming min will always act against the max interest. And we will see in the max node, here you can see in this figure, this is the root node, that is A. Then this it is max turn. So max chooses the maximum value. There are three children, B, C, and D. And the min node, that is the min term that chooses the minimum value. So max tries to maximize the utility while min tries to minimize the utility. And here you can see the utility values at the bottom of this figure, that is 3, 12, 8, 2, 6, 45 and 2. And these are utility values of max obtained from the utility function. And then first you can see that first, there are three children for the root node, 3, 2, 2. Then again we have child nodes. So we are always starting from the bottom. So if you are considering this part, then you can see that here the minimum, this is the minimum operation will work. So that is min will choose the minimum value 3, 12 and 8. So it will choose the minimum value, that is 3. 3 will be chosen. So min chooses minimum, that is here in the case of next case, that is 2, 4, 6. Then 2 is minimum. So it will select this one. Then minimum chooses 14, 14, 5 and 2. Here the minimum is 2. So here this path will be selected. And here you can see here B is equal to 3 and B, then C is 2 and 3 is again 2. So then the max chooses the action A1. So max best move is A1. So because it leads to the highest maximum value. And means best reply is B because minimum always select the lowest value. So that is min always select the lowest value. So the min max guarantees the best possible outcome for max assuming optimal play by min. Min-max tells us how good a position is, assuming both players play perfectly. So min-max of n, we can say it as the value of state n for max. So that means value is always from the max perfective. So even at means not. Here we can see some points. Given a game tree, the optimal strategy can be determined from the min-max value of each node. So here we have 3 points. Every node gets one number and that number tells how good the position is, and the best move will be move with the best min-max value. So once every node has a value, choosing a move become easy. So both players play optimally. So max tries to maximize and min tries to minimize. So no mistakes assumed. And min max does not model beginners. It models perfect opponents. So max means maximum value and min means minimum value. So max wants the best case and the min wants the worst of max. Then, for example, we can say that if here you can see that min-max of S is equal to utility. Then if the game is over, no more moves and value is already known. So that means win is equal to +1, loss is equal to -1 and draw is equal to 0. Then the case 2 is min-max of S is equal to max. So then min-max of result S comma A. So if it is max turn, the max will choose the action that leads to the highest minimax value. So max look at the children and picks the maximum. And the third case, that is min-max of S is equal to min-max of result S comma I. So if it is min's turn, min will choose the action that lead to the lowest min-max value. So here we are computed min-max values for min nodes. They propagated them to the max nodes. So min-max search utility values to terminal states and propagate them upward using minimum at min nodes and maximum at max nodes. The slide shows how the min-max actually makes a decision at the root of the game tree. So we already seen this figure. We will explain with that figure. So the decision is based on worst case analysis. So the max assumes min is perfectly rational. So here we can see the step one is assign utility values. So in the figure we can see that there are utilities values for the terminal nodes. So these values comes from the utility function and these values are always for max. So here we can see here the highest value will be the better for max and lower value that will be better for min. So first we can go to min node B. So here the child nodes are 3, 12 and 8. So the min will choose the move that is worst for max because he is the opponent. So he will choose the worst for max. So max better value is highest value, min better value is lower. So min will choose the move that is worst for max. So that means that will choose the minimum value. So minimum of 3, 12 and 8. So 3 will choose. Then similar to that in node C there are 2, 4, 6 are the three values and the minimum is 2. So 2 will be selected. And then for the node D, there is, you can see that here the values are, child nodes have values 14, 5 and 2. The minimum is 2. 2 will be selected. So here the min node will select the minimum values. Then next is max, that is root node. So evaluate the root max node. So the root is a max node. So max chooses the highest minimum value. So here you can see there are for this node A, that is the max. Here the child nodes are B, C and D. Their values are 3, 2, this is also 2. So it will choose the maximum value. The maximum is 3. So it will choose 3. So here we will see the min max decision at the row. So here we can consider at node A, action A1 leads to value 3 and A2 leads to value 2 and A3 leads to the value 2. So action A1 is the optimal chance for maximum. We already discussed that is it will choose the maximum value. So A1 action is chosen. So the min-max decision at the root select the action with the highest min-max value. Then max is actually not trying to get the best possible outcome. It is trying to avoid the worst case. That means min will always respond in the most harmful way. So max choose the move that gives the best worst case outcome. So we can say that min max maximizes the minimum payoff that max can guarantee. So this is the way the min max algorithm will work. Then we will see the min-max algorithm in detail. The min-max algorithm computes the optimal decision for max from the current game state. It tells max with the move to choose and assume the opponent min plays optimally and guarantees the best possible worst case outcome. So the min-max looks ahead in the game tree, evaluates all possible outcomes, and then choose the safest move. That means it explores all possible future moves and evaluate the end state and propagate values backwards. So we can say that there is a recursive nature. So recursive computation will be min-max is recursively work. So the value of a node depends on value of its children. And the same logic applied at every level. So the algorithm keeps calling itself until the game ends. So recursion goes down to the leaf nodes, and leaf nodes are the terminal nodes, and utility values are known at leaf nodes. We have already seen the utility values, and min-max always goes to the bottom of the tree first. We already discussed the working, so we have seen that it will always start with the utility values of the terminal nodes. And once the recursion reaches leaves, then utilities values are returned, and the minimum nodes take the minimum, and max node take the maximum. So we can say that we have to go down, evaluate, and come back and dissect. First go deep, then come back and make the decision. So the main application, min-max, is used in chess, checkers game, tic-tac-toe. So all these two-player games, we can use this. So here we will see different functions used in min-max algorithm. So first we will see the function, that is min-max underscore decision, that actually decide which move max should make at the root. And here you can see actions of S, that all possible moves max can make, and result state comma A, that actually state after making a move A, and min underscore value, that actually decides how good that state is, assuming min plays next. Then argument max, that actually choose the action with the highest value. So the min max decision returns the action that leads to the best guaranteed outcome for max. Next is max underscore value function. So this is actually how the max is thinking. So if this is a terminal node, then if the game is over, then it returns utility value. That means no further thinking is needed. And here we are taking v as minus infinity. So the max is looking for the highest value. And we have to do the action. That means if for each move, what will max will do, we will ask. What will the min will do. So then max will select the action with the best outcome. So each time the max takes an action, it will ask what will max do next, then it will select the action with the best outcome. So the max value computes the best achievable utility, assuming optimal play by min. Next function is min underscore value function. So here min is the opponent. We know that min value actually wants to reduce max utility. So here terminal state, if it is a terminal state, it returns the utility value, and here we are setting v as plus infinity and evaluate all possible moves and choose the minimum value. So the min underscore value assumes max will play optimally and choose the move worst for max. So here min and max are opponents. So min will play, that will choose the actions that move worst for max, and max will choose an action that will be worst for min. So min underscore decision method. So that calls the min underscore value function, and min underscore value function will call max underscore value function, and then max underscore value function will call min underscore value function until a terminal state is reached. So then values are returned, and it will be propagated upwards, and final decision is made at the root. So here you can see that it returns the action corresponding to the best possible move. That is the move that leads to the outcome with the best utility, under the assumption that the opponent play to minimize utility. So here it return action gives maximum guaranteed utility, and we are assuming that min is play optimally. So the whole game tree explode here. That means algorithm goes all the way to the leaves, and that's why min-max is expensive actually. And we have seen the argument max. There is a notation argument max, the action that gives the maximum value. So in the previous example, we have seen that there is A1, A2, A3 are the action, and A2 corresponding utility A1. If you are doing A1, then the utility value will be 3, and A2 it is 2, and A3 will be 2. So it will always select the maximum value. So 3 will be selected. So that means from the root node we are moving to B. In the previous uh, picture we have already discussed that. So that is the role of argument max. So we can say that the min-max algorithm recursively explores the entire game tree, applies the utility function at terminal state, and backup values using min and max operation and select the optimal move for. Then we will explain with an example. So this is the uh, picture we have. You can see here the graphical picture. So A has two child nodes B and C, B has two D and E, C has two F and G, D has two child nodes H and I, and E has two J and K, F has two child nodes L and M, and G has two N and O, and their utility values are given for the terminal nodes. So here, first we have to make at level 0, we are putting it as, this is level 0, max, and then alternative layers, then max, like that it will go. So then the min max alternates between maximizing and minimizing at each level. So here the terminal nodes have utility values. It is given in the question itself. These actually come directly from the utility function. So we have to no need to do any calculation. It is given. So then we will start with the from the terminal node only we are starting. So we are starting this level. So this level we have maximizer. So first case, the first node is D. At node D, it will check the child nodes. You can see here -1 and 4. So this level it is max, so it will select the maximum value, so it will choose 4. So that's why here it is written 4. Then next E, so E also choose the max this level itself, so it will choose the maximum value. It has two child nodes with utility value 2 and 6, so it will select 6. It will select 6. Then next node is F. F has two child nodes L and M, and this is also the max node. So here it will select the maximum value, that is -3 will be selected. Then next is G. G has two child nodes 0 and 7. It will choose the maximum value, that is 7. So then next we are moving up to the next level. It is min nodes. Here min nodes B and C. So B has two child nodes D and G with the values 4 and 6. So min level, so it will choose the minimum value. So here 4 will be selected. 4 will be selected. And for C there are two childs -3 and 7. So minimizer will choose the minimum value. So -3 will be selected. So now min always choose the value worst for max. Then finally evaluate the root node. At root node is max. Then there are two children B and C with the utility values 4 and -3. And this is the max node, so that it will choose the maximum value 4 and -3. Which one is maximum? That is 4. So now we have the optimal path. You can see here A to B, B to D, then I. So we are following this path. You can see. So this is the optimal path. Here you can see max chooses A to B and min chooses B to D and max chooses D to I. So this is the best guaranteed outcome for max assuming min plays optimally. So the alternation of maximizing and minimizing at the alternate lie corresponding to the opposing strategy of the two players. So max tries to maximize the score, min tries to minimize the score. So this alternative behavior gives the name min max. This part we have already discussed in the previous slide. We will see the properties of min-max algorithm. First one is complete. So min-max algorithm is complete. It will definitely find a solution in a finite game tree. So min-max explores all possible game states. If the game state is finite, it will always reach the terminal state. Therefore, it will find an optimal solution. So min-max is complete only for finite game tree. So then next point is optimality. So min-max algorithm is optimal if both opponent play optimally. So max chooses who's assuming that min will always respond optimally, and min always tries to minimize max payoff. So the decision guarantees the best possible worst case outcome. So that means min-max is optimal because it maximizes the minimum guaranteed utility of max. Next point is time complexity. That means time complexity is big of b to the power m. B is the branching factor. M is the maximum depth of the game tree. And min-max performs a depth first search. It explores all the nodes in the game tree. So the total nodes will be b to the power m. So this exponential growth is why min-max become impractical for large games like chess. So the time complexity of min-max is big of b to the power n, where b is the branching factor and m is the maximum time. And then here maximum depth. Then next is space complexity. Space complexity of min-max is similar to DFS. That will be a big O of b into m. Next, we will see the main drawbacks of the min-max algorithm is that it becomes very slow for complex games. Min-max explores all possible game states. For complex game like chess, the number of states is enormous. So the time goes exponentially. So if the branching factor is high means depth of the search increases quickly. So so the total states will be b to the power m. So that will be very high. So then reason for slowness we can consider it as large branching factor also. So for each position there may have many possible moves. So the game tree grows very fast. So even small increase in the depth makes the min max impractical. And then here the min max actually takes too much time. It cannot search deep enough, and then in such cases is it is unsuitable for real time game playing without optimization. So uh, there are so many limitations for the min-max algorithm, but the limitations of min-max algorithm can be improved using alpha-beta pruning. Alpha-beta pruning cut off unnecessary branches, and these branches cannot affect the final decision. So, and reduces the number of nodes evaluated. So, alpha-beta pruning does not change the result of min-max; it only makes it easier or faster. Thank you.